All right, so um, first let me discuss the material. Um, I wrote this in email as well that the chapter 4 we have 4.1, 4.2, and 4.4. Uh, from 5, I have 5.2, 3, 6, and 9, right? Uh, in 6, I have 6.1 and 4, and 7 has 2 and 5. So, sorry, just leave it. So, here, uh, in chapter 4, basically, I had a few things. One was increase, decrease, where the functions are increasing, decreasing, and basically in section 4.1, this was in section 4.1, and we also had concavity there. Yes. Okay. Yeah, it was in the assignment 3.2, but if you want, I can still include in the exam. If you want, I can just drop it. Student. Okay, so do you want to include this? Okay, so why? So just stick what I'm saying now, right? Uh, in assignment there is 5.8 as well, but here I removed that as well. Okay, so uh, so you can expect what type of questions you can expect in you know that in increase decrease of the function, uh, where is this? You all admit, 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 admit. All right, so some requests were pending, so I'm accepting them first. Okay, so now you see in increase decrease we work with all f prime of x. Okay, if f prime is positive, so work with f prime. For concavity we work with f double prime, right? F double prime gives you concavity upward downward. So what you have to do is if they ask you to find intervals on which f is increasing and the intervals on which f is decreasing, okay, what you have to do, you need to first of all get the points where for this thing there are step one is you have to uh, find the points where your first derivative is zero, because for increase I need f prime to be positive. Why I cannot change this? Okay, so maybe. All right, so f prime positive. I need f prime to be positive, and here we need f prime to be negative for decrease. Okay, so first instead of getting positive negative, let's just do the zeros first. Okay, let's see where it is zero. So if f prime is zero, and get the values x is equal to x1 x2 whatever the values you are getting, these gives you the separations on your interval. Okay, These are the intervals where you may change from increase to decrease, decrease to increase, like this. So these are your intervals. You can write interval 1, 3, 4, whatever. Okay. Then what we do, we make the intervals, we write intervals 1, 2, 3, 4, so on. We pick test points within the interval. Then we check the sign of f prime, whether it's positive, etc. And if you get positive, just write increasing there. If you get negative, just write decreasing. Positive, again write increasing. Okay. So this is actually the criteria. If you are working with concavity, do the same thing but with second derivative. If they ask you to find intervals of increase or intervals on which f is concave up, concave down, is concave up, concave down. If they ask you this, then I will do the same thing, because concave up means where your second derivative is positive, concave down means your second derivative is negative. So whenever they ask you about concavity, we need f double prime. So again, I will set the same thing. We will repeat the same thing. Set f double prime equal to 0 and find the values of x. Again, whatever values you are getting, x1, x2, etc. So this will again give you the separations of the interval. So you get the interval 1, 2, 3, so on. I will repeat the same thing which I did with increase, decrease, but I will only replace, you see, the third column will be replaced by f double prime. All other things will remain the same, and at the end our conclusion will change. So again we will write intervals, whatever intervals there are, intervals 1, 2, 3, so on, right? We will pick the test points, but then we will test second derivative, not the first one, for concavity. And if second derivative is positive, we will say that f is concave up. If it is negative, we will say that it is concave down, and etc. Okay. So see, exact same calculation, mathematical calculations, but we are getting different conclusions. So if I pick a question, page after, so if I pick a question here, for example, here is the book, and let me check which questions I gave you in assignment. I think I have assignment here. Okay, let me. So I can go to exercise and pick something. 4.1, we had, let's say, question number 15 to onward. We did, if I do, let's say, question number 19, it gives you all concepts here, because they ask us everything. 3x 4 minus 4x3, and they ask us everything. Find the open intervals, find the intervals on which f is decreasing, f is increasing, open intervals on which f is concave up, concave down, and at the end points of inflection. So increase decrease is easy. This is increasing, this is decreasing, right? We know that. So, but concave up, concave down are different. So this is concave up, this is concave down here. Concave. So the points, these are the points where the concavity is changing from concave up to concave down. So these points are called inflection points, okay, or points of inflection. So they ask us this at the end, what are the inflection point? So at this point your second derivative is 0. For concave up, second derivative positive. For concave down, second derivative negative. So this is the point where second derivative becomes 0. Also the concavity changes there. So these are basically 5 things they ask: intervals of increasing, intervals of decreasing, intervals where concave up, intervals where concave down, and inflection point. These are the 5 things they ask: A, B, C, D, and E. So I will do A and B together, of course. So for A and B, for intervals of increase and decrease, they both will be answered in one go. So what we will do, I will find the first derivative, which is 4 times 3 is 12x cubed minus 4 times 3 is 12x squared. So if I set it equal to 0, 12x squared is common into x minus 1. So if I set f prime x equal to 0, this will give me 12x square into x minus 1 equal to 0. So from here your x will be 0, and from here your x will be 1. So I got 2 points, 0 and 1. So my intervals are, this is the first interval, second interval, third interval. So the intervals became minus infinity. See, I start from minus infinity to 0, and at the end we have infinity. So my intervals, I will write these intervals in first column. First interval is from minus infinity to 0. The second is from 0 to 1. And the third is from 1 to infinity. Okay. So from this line, you can easily check. First interval is from minus infinity to 0. Then from 0 to 1. And then from 1 to infinity. So these are the 3 intervals. Now I will pick the test points from here. So what I can pick from this interval? Minus 1, any point within the interval. Here I can pick 1 by 2, and here I can pick 2, right? So these are the points. You can pick any other points as well who are in the interval, but these are the simple choices. Now I will put it in first derivative. First derivative is 12x square into x minus 1. So if I put x equal to minus 1 here, it gives me 12 into minus 1 square minus 1 minus 1. So this will become negative. Minus 24. Okay, so this is negative, less than 0. Now here at 1 by 2, it is 1 by 2 square, and 1 by 2 minus 1. This is again negative. Uh, and if you do the third one, that will become positive, 2 minus 1. So this is positive. If you calculate them, these are positive and negative answers. So at the end, I can write f decreasing here, it's negative, again decreasing here, and increasing here. Okay, so now I can combine these two intervals because they are both decreasing. So f is decreasing on minus infinity to 1. So I can close the bracket, and here from here I can write f is increasing on f is decreasing on minus infinity to 1, and f is increasing on 1 to infinity, and we close the bracket. Okay, we do not close bracket here, we write open intervals because we are checking only the points within this. 1 are not included, 0 are not included, but when you write the conclusion, then we include these 1 and 0 as well. Okay, so this will become a closed interval. So this is the answer to question number A and B. I have give both answers directly in same. If I exactly repeat the same thing with second derivative, I will get the answers for C and D for concavity. So let's say if I want to answer C and D, then C and D part are for concavity, I will find the second derivative. What was the first derivative? First derivative was 12x cubed minus 12x squared. Okay, so now if I take the second derivative, it will become 12 times 3 is 36x squared minus 12 times 2 is 24x. So 12x is common. So 12 3x minus 12 2 are 24. So this is what I got. So now if I set f double prime x equal to 0, I will get 12x into 3x minus 2 equal to 0. So first term will give you x equal to 0 and second term will give you 2 by 3. Okay, so this gives me x equal to 0 and this gives me x is equal to 2 by 3. So now my intervals are, see, I got 0, but now I do not get 1, I got 2 by 3. Okay, so now again I got 3 intervals from minus infinity to 0, from 0 to 2 by 3, and 2 by 3 to infinity. You have to keep the position there. Okay, you don't write from 0 to minus infinity or from 2 by 3 to 0. You have to go from left to right. Interval goes from left to right. Okay, so the first interval is from minus infinity to 0, and then from 0 to 2 by 3, and then from 2 by 3 to infinity. Now if I pick test points will be x is equal to minus 1, x is equal to 1 by 2 is still there because 2 by 3 is bigger than 1 by 2, so 1 by 2 will be somewhere here. And then I will pick x is equal to 1 because now 1 is on the right side. You can still pick 2, but 1 is fine. It's easy choice. We go with the easy choice. Now the second derivative is 12x into 3x minus 2. So if I put x minus 1, it gives me 12 into minus 1 minus 3 minus 2. So minus 5 into minus 1 gives me positive number. I'm not interested in the answer. I'm only interested in positive, negative. So that's enough. That's why I'm not calculating. If you calculate from the calculator, it's okay. Write the answer and then you can say it is positive or negative. 12 into 1 by 2, positive. But 3 by 2 minus 2 is negative. So again, this will become negative. And 12 into 1 and 3 minus 2. Now this is positive. So see, it means f is concave up here because its second derivative is positive. Concave down here because second derivative is negative. Again concave up here. Okay. So now I got two intervals for concavity upward and one concavity for downward. So now I can write f is concave up on first interval is minus infinity to 0 and second interval is from 0 to 2 by 3 to infinity. So these are the two intervals where my concavity is upward, the first one and the last one. So I cannot combine them, right? And f is concave down on which interval? From 0 to 2 by 3, the middle interval, this one. Okay, so here the concavity is downward. So here you do not close the interval. Remember, for increase decrease we close the interval. You see, I wrote closed interval from 1 to infinity. Infinity is never closed, the numbers are closed. But for concavity up and down, you do not close the interval. The last part is E. What are the inflection points? So inflection points are those where your concavity changes. Okay, second derivative is 0, so 0 and 2 by 3, and concavity also changes here. You see, when I was passing through 0, the concavity was upward, but after that it becomes downward. So it means this is an inflection point. Now concavity is downward before 2 by 3 and after that it again becomes upward. You see here. So concavity changes at 0 and 2 by 3. So clearly from B and C, I can write clearly from calculations above, from C, D above, I can say that F has inflection points at, or points of inflection, it is the same thing, points of inflections or inflection points at x is equal to inflection points at x is equal to 0 and at x is equal to 2 by 3. So at both the points I have inflection point. If concavity does not change, then it will not become inflection point. So remember, even though my second derivative is 0 here, but if they do not change their concavity, they do not become inflection points. Okay, like here you see 0 is a critical point. My function was decreasing, it is still decreasing. Okay, so if the sign does not change for the second derivative, it does not become a inflection point. So this is the whole summary of section 4.1. So you can expect one question like that. I will give you a function and I will ask you find the intervals of increase decrease or find the intervals of concavity up and downward. Okay, I may not ask you to all the things. I may ask you all things as well, but if I will see if the exam is too lengthy, then I may ask you one of them. Okay, so if I ask you only the intervals of concavity, you will work with second derivative. If I ask you intervals of increase decrease, you will work with first derivative. Okay, any questions so far? Yes, guys, any question? It's clear, right? So then if you go to 4.2, it is the same thing as you got intervals of increase decrease. Let's say your function is increasing somewhere. After that, it starts decreasing. Then you see I have touched this maximum point. Okay. Now it was decreasing and it again started increasing. Then I touched the minimum point. Okay. So this is the relative maxima, this is relative minima. We call it relative maxima, relative minima. Okay, let me write the full name. Relative maxima, and this is relative minima. It may not be a maximum value of your function. In its own neighborhood, this is the maximum, the topmost value nearby, the lowest most value nearby. So see what is happening on the left. Your function is increasing on the left and decreasing on the right. Here your function is decreasing on the left and increasing on the right. Okay, so for minima your f decreases on the left side, okay, and increases on right side. If this type of thing happens, it means you have relative minima over there. And here you see at relative maxima you have the opposite, f increases on left and decreases on right. If this type of thing happens, then you have maxima there. So you see, mathematically it is the same thing that we did here. You see, it is the same thing that we did here. What is happening at 0 and 1? What is happening to the left? What is happening to the right? You see, it is positive. So my function, if I look at the previous example, right? In previous example, I had 0 and 1, and at these points another thing happens is f prime becomes 0, f prime becomes 0. So these are the points where you can get maxima and minima. So in previous example I got f prime, f decreasing on the left because f prime was negative, again decreasing on the right. So see, it did not change, so my critical point did not become maxima. But here you see my function was decreasing and then it started increasing. It means I have a minima there. It was decreasing, still decreasing, so nothing here. At 0, I got nothing. Okay, so we can say that f has minima at x is equal to 1, and at 0, I got nothing. No maxima, no minima. Because it was decreasing, still decreasing. So the points where either f prime is 0 or f prime does not exist. Okay, the points are called critical points. Okay, if the first derivative is 0 or does not exist, they are called the critical points of f. And your maxima minima only occur at the critical points of f. So this is the note: relative maxima minima only occur at critical points. So we only look at the critical points, we do not look here and there. So if I have to solve this thing, what I will do, I will repeat the same thing. Let's say if the question is here, find the maximum minima of this function. What I will do, I will take the first derivative, put it equal to 0, get the critical points. If there is any point where your function does not exist, I will get that as well. But polynomials, they always exist everywhere, so there is no point where f prime does not exist. So I got, again, I will write left of 0, right of 0. So maybe instead of that, you can write this is called the first derivative test. Okay, this is called the first derivative test for maximum minima, when we look at what is happening to the left, what is happening to the right. Okay, so let's say I can do an example. In 4.2, I think, what did I ask? Uh, Find the relative extrema using both first and second derivatives. I don't know what question I asked, but I can maybe open the assignments. Some students sent me some questions as well. I don't know who was that. Let me check. Um, where is the assignment? I opened it up. I'm checking a message. I think I got a message yesterday with some questions. Some student asked me a question that please do these questions. Yeah, here. Question. So 33 in first one is difficult. What I did from 4.1, what I did here, you will get something similar to that. Okay. I will not give you a very difficult function like sine x, cosine x. Sine, if I ask you sine, cosine, I will only ask you one, just sine or just cosine. I will not ask you the combination of both. Okay, that becomes little difficult. So don't worry about that. If you can repeat this question with similar function, maybe if I change the power, it does not make it different, right? If I give you 4x cubed minus 3x squared, right, it is the same thing. So these type of questions you can expect. In 4.2, let me pick a question which is also given in the assignment. In 4.2, I gave you 9, 25, 34. So let me do 34. X4 minus 12x cubed. 4.2, number 34. Fx is given x4 minus 12x square cube. Okay, so the question is find the relative extrema. Relative extrema means both maxima minima. Extrema means both maxima minima. Okay, max min. For these both we call them extreme values. Maximum minimum values are extreme values. So for extrema, if I use first derivative test, I can take the first derivative, which is 4x cubed minus 36x square. So if you put it equal to 0, I will get 4x square common. So I will get x minus 9 is equal to 0. So x is equal to 0 and x is equal to 9. So now what I will do, instead of writing the intervals, I will write left and right values like x less than 0, x greater than 0. But at the same time, x less than 9 and x greater than 9. So you can write it like this because it looks more to the left and to the right instead of writing the intervals. Otherwise, we can write intervals as well. You see, uh, x less than 0 here, and to the right of 0 up to 9. So I can write the second this, and then x greater than 9. Okay, so now again I will pick the test points, same thing which we did in the previous example. So if you pick test point on the left of 0, minus 1, between 0 and 9 we can pick 1, and after 9 we can pick 10. Okay, you can pick anything, 2, 3, 4, 5, 6, 7, 8, whatever you want you can pick. Then f prime is 4x square into x minus 9. So if you put minus 1, it will become 4 into 1 and minus 10. So this is negative. If you put 1, it is 4 into 1 and minus 8. It's again negative. Then 4 into 100 into 100 minus 9, 91. So that is, 10 minus 9, 1. Okay, so this is positive. So you see, now f is increasing, decreasing to the left of 0, still decreasing to the right of 0, but now it is increasing. So see, I got nothing here, but from here I got relative. See, before 9 it was decreasing, after 9 it started increasing. Before 9 it was decreasing, after 9 it is increasing, so we got a minima there. So I can say that f has a relative minima at x is equal to 9. Okay, so nothing, I got nothing at 0, so I will not say anything. I will not say that at 0, because before 0 it is decreasing, after 0 it is again decreasing. So when it is decreasing or increasing case, there is nothing, no maxima, no minima there. Okay, so not all critical points will become maxima and minima. So your function was decreasing, it became constant, again it started decreasing, and then it started increasing. So you see, you only got a minima, no maxima here, even though f prime was 0 here, but it did not become a maxima or minima. Okay, and here it becomes a minima. Right? This is what happens here. This is the first derivative test. Now if you use the second derivative test here, what is the second derivative test? Second derivative test for maxima minima only concentrates on the critical points. It does not look at the left and right side. If there is a maxima at some point where f prime is 0, then I only check at this point where second derivative is positive or negative. If second derivative is negative, it gives you a maxima there. Okay, and similarly if you have a minima where first derivative was 0, but if your second derivative is positive, it means concavity is upward and we have a minima there. You see, when concavity is upward we pass through a valley, if concavity is downward we pass through the top of the mountain. Okay, so this is the second derivative test, but here if f double prime becomes 0, the test fails. This is the problem with the test. The test fails and we go back to the first derivative test. This is the problem here. Okay, so it's something sad. So this is an easy test, but it sometimes fails. So for example, in above example, we know that my f prime x was, what is the f prime x in above example? 4x cubed minus 36x squared. So 4x cubed minus 36x squared. If I take the second derivative of x, it will become 4 times 3, 12x squared minus 72x. Okay, I'm not putting it equal to 0. We got this because we are looking for maxima minima. They only come from the first derivative, critical points. So I know that I got these points 0 and 9. These are the 2 points. So these are your critical points, still the same, which I solved above. 0 and 9. But now I will replace these critical points in second derivative. Put in f double prime and see whether they are positive or not. So if I put this in second derivative, I will get 0 minus 0, which is 0. So you see, test fails. I cannot say that there is no maxima minima there. Test fails here. Okay. So what we do, it means go back to first derivative test. Go back to first derivative test and see what is there. Okay. This is the issue with this test. Sometimes it fails. If I put 9, it will become 12 into 9 square minus 72 into 9. So uh, 12 into 9 square, let me see, calculator. 12 into 9, so that is 972, and minus uh, 324. Okay, 324. So it means it's positive, you see, right? So that is positive. Whatever the answer is, it is. No, the final answer is 324. The final, okay, the final answer is. Okay, no problem. The final answer is 324, which is positive. So we know that when it is positive, then it is minimum. You see, we wrote that here. When your second derivative is positive at a critical point, it gives you minima, this situation. Okay, so from here I can say that f has relative minima at x is equal to 9. So this test is easy, but sometimes it fails. So when it fails, we have to go back to first derivative test. First derivative test never fails. Okay, first derivative test never fails. Test fail means I do not know whether there is a maxima minima or it's not nothing. Okay, so we go back to first derivative and then check what is happening to the left and to the right, and from first derivative test I know that there is nothing at x is equal to 0. Okay, so these are the two tests which can be conducted for finding relative maxima minima. First derivative test is simple because it is the same as finding intervals of increase decrease. Once you find the intervals of increase decrease, then okay, so now you see everything. Okay, uh, let's see what other questions she asked. In section 5.2, 35, 6.47. Okay, as if I reach there, I will answer that as well. Chapter 5 has integration. So you should remember all the integration formulas. Okay. Um, these type of formulas we should remember. Integral of 1 over x dx is natural log of x. Yes. Okay, 4.4 I missed. That's what you are looking for, right? So you have these formulas, lot of them, right? You have to keep them in mind. Uh, if I ask you some difficult formula, I may give you in the book or in the exam, or I may write it on the board for you. But these type of formulas you should remember. Okay, if you have just e to the power kx, we know that e to the power kx is the same as e to the power kx, but we divide by k. Uh, So only this k will get divided. This k. Okay. I don't know whether I can change the color. I don't know why I cannot select the other colors here. Something is wrong. But anyway, this k comes down. So now, what else? We have sine, cosine functions. Sine is minus cosine, cosine is sine, and every time we add a c. So these type of formulas we have, sine x plus c, etc. So now, if we are looking for 5.2 contains only these type of formulas, means I can give you a combination of these integrations. For example, question number in assignment 3 5.2, I think I have question numbers 1 2 10 14, 1 2 10 14, 10 14. See, these are simple. If I go to 10, it is cube root of x square dx. So I cannot do it directly. So I have to write this as a power. X square is there, and you know that cube root means divided by 1 over 3, right? Power 1 over 3. So now if I write this as 1 power, it is x to the power 2 by 3 dx. So we have to manipulate integrand a little bit, and now I can use this formula, the power formula. So this will become x to the power 2 by 3 plus 1 divided by 2 by 3 plus 1 plus a constant, right? So that's how we can integrate these type of functions. If there are more than one questions there, uh, 14, yeah, 14 has a lot of them. Now you can simplify. 2 by 3 plus 1 is 4 by 3, 5 by 3. So this will become 3 by 5 x to the power 5 by 3 plus c. So this is your answer. Now if you do 14, there is 10 over y to the power 3 by 4 minus cube root of y and plus 4 over square root of y. If you have this thing, then I will use the properties of integration. Properties of integration say that you can 10 is a constant, so you can write the first integration separately, 3 by 4. I can bring it up. I can write this as y minus 3 by 4. Okay, dy dy, not x, minus integral of this cube root of y is 1 by 3 dy, and then plus 4 is constant, and integral of 1 over square root of y, which is minus 1 by 2 dy. Okay, so we should bring them up. We should bring them up to make the power. So I should move them up. Okay, so now it will use all the power rules. Minus 3 by 4 plus 1 divided by minus 3 by 4 plus 1. Okay. Okay. Minus y to the power 1 by 3 plus 1 over 1 by 3 plus 1 plus 4, this is 10, plus 4 y to the power minus half plus 1 over minus half plus 1. And at the end just write 1c. Just 1c is enough at the end. Okay. So now if you simplify, minus 3 by 4 plus 1 is 1 by 4. So that will become 40, and y to the power 1 by 4. Then this 1 by 3 plus 1 is 4 by 3. So this will become 3 by 4 y to the power 4 by 3. And this is 1 half. So this will become 8 y to the power 1 half plus. Okay. So that's your answer. Simple. So these type of simple integration, you can expect couple of questions like that, okay, where I can ask you these type of simple questions. um, I may then go to 5.3, which is integration by substitution, right? I can mix them up with other functions as well. Maybe I can give you one power rule. I may give you something like x to the power something, right? And then I will write e to the power something, okay? And I can give you one sine x here and dx. So here in same question, I can ask you three different formulas, right? So you should remember how to implement x power rule, how to implement exponential, and what is the integral of sine x. So you can write them separately. You will first of all write them separately, dx plus integral of sine x dx separately. And now I will use the formula. Whatever power is, I will use the power rule. Ex is ex, sine x is minus cos x plus c. Okay, so these type of things you can expect, where I can combine different formulas. 5.3, one question from here as well. It is a substitution. 1.3 plus 1.9 both. 5.3 and 5.9. Sometimes you have a function and inside you have another function, but inside function has the derivative there with dx. Okay, and in 5.9 we have the same thing but with the limits a to b, f of g of x, g prime of x dx. So we look for a function whose derivative is inside, whose d by dx is inside. If this type of thing happens, then we substitute u is equal to g of x, so that your du becomes g prime x dx. Okay, so if I do that, this integral becomes integral of f of u and du, because this whole thing becomes du. Okay, and then you can integrate this, whatever your answer is, you can integrate and then put your u back, g of x. Okay, but here in 5.9, when you substitute, then this becomes f of u du, but now it has limits, so I will change the limits as well. If limits are given, then this is the extra thing. After doing this part, okay, we will do another extra thing, which is if x is a, then u will come from your substitution g of a. I will put x is equal to a here to get the value of u. Similarly, when x is b, it will give me u is equal to g of b. Okay, so whatever that number is, this number may be c and this number may be d. So you will change the limits from c to d, limits of u, and then you will integrate. If your answer is f of u, from c to d, we will just put d and we will put c in it. So f of d minus f of c. So I do not need to go back to x. Why? Because I have changed my x to u and we change the limits as well. So no need to go back to x. Here you see, at the end I give the final answer in 6. So I will do something. How we got this one? How we got this one? This is section 5.6, fundamental theorem of calculus. So I will do some problems after that. Fundamental theorem of calculus. What is that? If I am integrating from a to b fx okay, do you have any question or anything? I think I got some notification here. So what you do, you integrate whatever f has the antiderivative, but then you use the limits. You put b first, you get f of b, and minus you put a, then it gives you f of a. Okay, first upper limit, then the lower limit. So this is only 5.6. If the limits are given, that's how you can integrate. For example, if they give you from 1 to e 1 over x dx, I know that the answer to 1 over x is natural log of x, but because limits are given, so I have to use the limits. So I will put e first, which is log of e, minus I will put 1, that is log of 1. So log of e mod is log of e and log of 1 mod is log of 1. So log of 1 is 0 and log of e is 1. So your answer is 1 minus 0, which is 1. So this is the fundamental theorem of calculus. That is your 5.6. Okay. So if I go to 5.3 and do some substitutions, I did lot of questions in during the class as well. So I can pick something from the assignments. Let's say from 5.3 I gave you 14915. So let's say 14915. Uh, in 1 and 4 the substitutions are given. So I think this is easy. But in 15 onward substitutions are not given to you. 15, 21, 35. So I can do something. Let's say if I do 35, exercise 35 gives me ex over 1 plus e2x dx. Okay, 35 is the part. Yes. So here you see the problem is I do not see anyone whose derivative is inside, but you see it is e to power 2x can be written like that. E to the power 2x is ex square. So ex can be replaced as u. Why? Because the derivative is still ex. This is the derivative. So if I substitute u is equal to ex, I will get du is equal to ex dx. So now you see I will get 1 over 1 plus u square, and ex with dx will give me du. You see, ex with dx will give me du. And now it is a formula that it is tangent inverse of u plus constant. 1 over 1 plus x square. Again, you see we have to remember the formulas. The formula for 1 over, if you look at your table, this is given in the table, as well as in section 5.2 these formulas are given. So now I will replace my u back. What is my u? U was e to the power x plus c. See, I replace the value of u back here. Okay, so that is my answer. So this is substitution, simple. If they give you the limits, let's say if I pick something else as well, 31, it's not the part of the assignment, but I can do that. E to the power sine x into cosine x dx. Now you see some part of the question, this sine x has the derivative cosine x dx. So why not replace u is equal to sine x? Not the whole function. You don't need to replace the whole function. Any part of the function whose derivative is with cos x. Okay. So du is equal to minus cosine x dx. Okay. I don't need minus here, so I can bring it to the other side. Minus du becomes cos x dx. Now it is e to the power sine x is u and cos x is minus du. So e to the power u du. Now you see it's very easy. I know that the integration of eu is just eu, the same thing. Okay, and now I can replace this u back. So if I replace this u back, it will become sine x plus const. So this is your answer. So that's how basically you do integration by substitution. Let me just write you that summary, that look for some function that may be inside some other function, or it is the part of some other function. Okay, some function. But important thing is, if you looking for some function, its derivative should be inside. Whose derivative should be with dx, whose derivative is there with dx. With dx, it's very important that derivative should be with dx. Okay, so see here where I wrote this one, you see the derivative is with dx. This is the part. Any function inside some other function, or it may be the same, the whole function as well. Okay, but the derivative should be with your Oh, sorry, I think I made a mistake here. Let me change it. This is the mistake. The derivative of sine is not minus, it is plus cos. The derivative of sine is plus, not minus. So don't write this minus here. No need. No minus sign here. Okay, no minus sign here. Sorry. Okay, so this is just du. So no minus sign. It is just eu e to the power sine x plus. The derivative of sine is plus cos. Integration of sine is minus cos. So this is actually, if you understand this thing, then you can never make a mistake. So if I pick some example with limits, then how only one thing will be extra, not a lot of things, just one thing will be extra. For example, if I pick 5.9 number 16, let's say this one, integral of ex 3 minus 4ex dx, and from 0 to log of 5. See, the limits are given. Now you see, if I choose this whole thing, the derivative is given ex with dx. Okay, so it means I can shuffle it a little bit. I can write 3 minus 4 ex before, and then I write ex dx together. These ex to ex dx together at that. Now you see the derivative of this thing is given. So I can replace u is equal to 3 minus 4 ex. The derivative of this will become 0 minus 4 ex dx. I only have ex dx, so I can divide by minus 4. I don't need minus 4 here. So this is gone. So I got minus 1 by 4 du is equal to ex dx. One thing is that now if you replace it here, it will become u, this will become u, and this will become minus 1 by 4 du. But now I have to change the limits here. I cannot bring 0 and log of 5 because my variable becomes u. So this is the extra thing you do in 5.9. You take x is equal to 0, the first value x is equal to 0, put it here. Put here x is equal to 0. You got u is equal to 3 minus 4 e to the power 0 is 1, so that is minus 1. So you see this value becomes 0 becomes minus 1. 0 becomes minus 1. Now the second value is natural log of 5. So u will become 3 minus 4 e to the power log of 5. E and log cancel each other. So you got 3 minus 4 into 5. So this is 3 minus 20, which is minus 17. Minus 17. Okay. So now this 1 by 4 is constant. I can bring it outside. So minus 1 by 4 outside. And it is from minus 1 to minus 17 and u du. So now if you solve it, it will become minus 1 by 4. U becomes u square by 2 from minus 1 to minus. Now you do not need to go back to x. You see in the previous example, when limits are not there, I replaced u back, right? We replace this u back. But now because we have changed the limits as well, I do not need to go back. I can just directly use the limits of u minus 1 by 4. If you put u minus 1 by 8, because I can multiply these two, 4 2s are 8. U square means minus 17 square minus minus 1 square. So this is your answer. So it will give you minus 17 square minus 1, whatever that is, just right. And 17 square is 289 minus 1 is 288. 288 by 8. I hope this is correct. So anyway, these are your All right, guys. So this is pretty much it in chapter 5. So you can expect 3 4 small parts from here. Okay. And remaining is just applications of your integration. If you know the integrations, you can easily do 6.1, 6.4. One thing which I mentioned, that this integral from a to b fx dx, if fx is continuous and positive, if f is continuous and f is greater than equal to 0 on your interval AB. If this is the case, then this gives you the area under the curve. Okay, which area? If fx is positive above x-axis and it is continuous, then this area is given by your integration. So this is an application that you can find the area by using the integration. In 6.1, it is area between two curves. If two curves are given, fx is at the top, gx is at the bottom. Okay, so to b a to b, then if you are looking for this area between two uh, curves, then it is again easy that you have to integrate from a to b, but you subtract upper minus lower curve, top minus bottom, upper minus lower, whatever you can see. You subtract the bottom curve from the top curve, top curve from the bottom, sorry, bottom from the top, or upper, lower from the upper, whatever you say. So okay, so I think you can do that if you want. I think I did a lot of practice during the session. I put the questions on the board on projector and did many things from there. So it's not difficult. 6.4 gives you the arc length, the length of arc. If you want to find the length of the curve from this point to this point, what is actually the length of this curve? Okay, from a to b, then what you can do, you can use this formula. It is still the integration, but not just fx, but the derivative of fx. If dy by dx square and dx, uh, this curve is given as y is equal to fx, so you take the derivative of the function, you replace it and solve it. So maybe let's say 6.4, I can pick something from the exercise if you want. I think I gave you only a few questions from there. 6.4 has 357. I did 5 in the in your class. So let's do the third one. Uh, if you open the notes from my lecture on 6.4, we did question number 5 on the board. You can see that. And if I ask you this question in the exam, I will not ask you something like problem number 7. Problem 7 is little difficult as long as the final exam is concerned. So this is easy. I can ask you something like this. And it says find the arc length of the curve from x is equal to 0 to x is equal to 1. So see, they gave us the limit. So a is given 0, b is given 1. Okay, so a is 0, b is 1 here. So now I will take the derivative first, because in the formula I need the derivative. So the derivative is 3 into 3x 3 by 2 minus 1 over, sorry, that's it, minus 0. So that will become 9x 1 by 2. 3 by 2, sorry, yes. 3 by 2 x 3 by 2 minus 1. So 9 by 2 x 1 by 2. So this is what I got. Now I can put it in the formula. So therefore the length of curve is from 0 to 1, 1 plus dy by dx square. So I can replace the derivative here. If you want, you can solve this thing outside. This square root 1 plus dy by dx square, we can simplify that outside and then bring the simplified version in the integration. We can do that as well. Square. So if I do that, it becomes 1 plus 81x by 4 dx. This is what I got. Okay, so here it will use substitutions because I have something in the denominator whose derivative is a constant. So what I can do, I can use this as u. So this is basically section 5.9. It is like a question in section 5.9, right? So I will substitute whatever you have inside the uh, square root, and the differential of that will become 81 by 4 dx. I don't need 81 by 4 because dx is alone, so I can send it over there. So this will become 4 by 81 du is equal to dx. Now this becomes 1 square root of u, and this becomes 4 by 81 du. Okay, but now I need to change the limits as well. So when x is 0, my u is 1, right? When x is 0, u is 1. And when x is 1, u is 1 plus 81 by 4, which is 85 by 4. So I got from 1 to 85 by 4. These are the limits now because 0 becomes 1 and 1 becomes 85 by 4. So we change the limits. Now 4 by 81 is a constant. I can integrate. This will become 1 by 2 becomes 3 by 2. 3 by 2 from 1 to 85 by 4. So now you can replace the upper limit minus the lower limit. So if you do that, it will become 2, 4, 8 and 3 ones are 3, 8 by 2, 43. And now if you replace 85 by 4 to the power 3 by 2 minus 1. So now just use calculator and find the answer. Okay, so that's how you can find the arc length of a curve. It's not difficult. You just have to remember the formula and just replace the derivative of the function in the formula, simplify the function and integrate. It may need substitution because we have studied chapter 5, so we can easily do that. What else we have? In chapter 7 we have two things. Do you have any commitment, any other class or anything like that? Can I work for 10 more minutes or do you have any questions before I go further? Oh, I will tell you at the end. Just suspense. I did not give a question from 4.4, so you can just concentrate on first two sections. Okay. Hamad, is it okay? So now I recognize your voice as well. So anyone else? Any other questions? So okay, in chapter 7 we have only two things. One is integration by parts and one is partial fractions. So 7.2 has integration by parts, and if you remember the formula, uh, it's not that difficult. You have to only choose what are your functions. If you have two functions u and v dx, right, or f g dx, I don't know what I used in the class. So you keep first function as it is, you integrate the second one, minus you take the derivative of the first function, integrate the second one, but we again integrate this whole thing. So the second part still needs integration. Okay, so for example, if you have x into sine x dx, right? Now I can take this as u and this as v. So u as it is, integral of v dx minus the big integral outside, the derivative of u integral of v dx. So basically what we do, you see, x becomes the derivative here, d by dx, and the second is the same. We do not change it, you see. Integral of sine x, integral of sine x is the same. Now x into integration of sine is minus cosine x. The derivative of x is 1, integration of sine is minus cosine x, and we are multiplying these two. Sometimes students write 1 minus cos x. 1 minus cos x is not there, it's a multiplication. So that is just minus cos x. So you got minus x cos x. This minus outside will make it plus, and inside you are just left with cos x dx. Now I can integrate the second one. So your answer is minus x cosine x, and cosine x has the integration sine x plus c. So this is simply integration by parts. You may have something like x into log of x dx. Let's see. Okay. Now if I take x as u and this as v, it will not work. Reason is x remains as it is integral of log of x dx. We do not know what is the integration of log of x. This is the issue. Okay. Integral of just log of x is not known to us. Okay. Not known. So that's why I will not take this as u. What I can do, I can take log x as u and this as v. So u as it is integral of v dx minus the derivative of log, right? Derivative of log integral of v dx, and then we integrate outside the bigger one. Now you will see it will work. Okay, this makes it difficult because log of x is there. X becomes x square by 2. But what happens here? X becomes x square by 2. So we can say that we are in bigger trouble. But at the same time, the derivative of log of x is 1 over x. So log is gone. So whenever there is a log inside your function, that is the choice for you. Okay. So now I got x square natural log of x by 2 and minus 1 by 2. I can bring 2 outside. And here simplify. X square by x is just an x dx. Okay. 1 over x into x square is just an x. So just simplify these two first because we have to multiply them. So simplify, it gives you x. Now the answer is x square natural log of x by 2 minus 1 by 2, and this x will become x square by 2 plus a constant of integration. So that is my answer. X square log of x by 2 minus 1 by 4. So x square by 4 plus c. Okay. Alright guys, so this is your integration by parts. I think it's easy. If they give you the limits in integration by parts, let's say if the limits are given in integration by parts, when you have this uv thing, uv dx, then u integral of v dx, and this whole thing goes from a to b. So when you put the limits will be put in everywhere in u and the answer here. And minus, because inside you are taking the derivative integral of v dx, and this still needs to be integrated, so we do not use limits inside, we use the limits outside here. Okay, never use the limits inside. This is something which is different than previously. So if I pick a question with limits, I can do that here. With limits, let's say question number 3, 6, 10, 23, 3, 6, 10, 23 do not have the limits. 30 and 32 has limits. So I can do 30. Okay. So problem number 30 has limits in 7.2. So this is from square root of e to e natural log of x divided by x squared dx. As I said, log of x is the obvious choice for your u. So I will take this as u. So I will rewrite it like this. I can write it as e to e natural log of x, and this 1 over x square can be written as x to the power minus 2 dx. Okay. So now I take this as u and this as v. So if I do that, u as it is, integration of v will give me x to the power minus 1 by minus 1. This is the integral of v, right? So this whole thing will go from square root of e to e. This whole thing, okay? Minus square root of e to e, and inside I will not use the limits. The derivative of log is 1 over x, and the second thing is as it is, x minus 1 by minus 1. and dx. Because I still need to integrate, that's why I did not use the limits inside. We will use limits at the end. So see, this log x becomes 1 over x here. Okay. So now this has become minus log of x by x, because this minus 1 and x to the power 1 will go down. I will use the limits separately here. Minus, minus minus plus, and inside you have, if I simplify, this is x minus 1, this is x1. So if I bring it up, it will become x to the power minus 2 dx. Okay, minus 1 is already there, and this 1 will go up, will become minus 1. And now I will integrate. Here you can put e, so minus natural log of e by e, and if you put this here, it will become plus log of square root of e by square root of e. This is what you got. Plus, here the integration is x minus 1 by minus 1, and again I can put the values. Now integration is done, so I can replace. So only replace it here. So I will replace only here now these two values. So I got log of e is 1, so I got minus 1 by e. Here I don't know what I can do. Log of square root of e can be written as 1 by 2 log of e. Why? Because this is power 1 by 2. This power is 1 by 2, right? So I can bring the power down. This is the property of logarithm. And log of e is 1, so I can write 1 by 2 here. So this will become 1 by 2 square root of e. And if you put e here, minus 1 by e, it will become minus 1 by e and plus 1 over square root of e. This is what you got. So you can combine these two, maybe this one and this one can be combined. It will become minus 2 by e, and this one and this one can be combined. 1 by 2 plus 1 is 3 by 2. So 3 by 2 e. So that is your answer. Okay. If you want to use calculator and write your answer in points, you can do that as well. No issues. Okay. So this is the integration by parts when the limits are given to you. One last thing, 7.5 is the partial fractions. Partial fractions become little difficult when you have quadratic expressions in the in your denominator. So what I can do to make it easy, I will only give you linear expressions, linear factors only. Okay, linear only. Linear are easy. If you have quadratic, it becomes little difficult. So I can ask you something with linear factors. So that is at the end of 7.5 in the exercises. If I pick, let's say, x square minus 3x plus 4, very similar to this question will be in your exam. Okay, what you have to do, this is a quadratic expression and I need to make factors. So partial fraction says that only pick this. Okay, just pick this, hold on, I don't know what is the answer, just hold on to that. So just write this inside function and make factors in the denominator. X minus x minus. Product should be minus 4, so it can be 1 and minus 4 or minus 4 and 1. Okay, but I need sum to be minus 3, so it will be plus 1 and minus 4. Plus 1 and minus 4, because sum will be minus 3. Now I will write these factors separately, x plus 1 separately and x minus 4 separately. So A for the first one, B for the second. Then what we will do, we multiply this by this one, this by this one. Okay, we multiply them. So if A gets multiplied by x plus x minus 4, B gets multiplied by x plus 1, and then the LCM is the whole x plus 1, x plus 4. So on the left side we have 1 over x plus 1, x plus 4. So it means I can cancel them. You see, they are the same thing, so cancel. So I got 1 is equal to ax minus 4 plus bx plus 1. These are only two things. Now I can take two values of x. I can choose any two values, but I will choose minus 1 and 4. Why I am choosing this? Because when I choose x is equal to minus 1, it gives me a minus 5, but it makes this 0. So I will directly get a is equal to 1 by 5. When I pick 4, then I will get a with 0 and b with 5. So if you divide by 5, you will get b is equal to 1 by 5. This is the reason to pick these two values. One of these factors will become 0 and I will get the a and b directly. So now I will replace these a and b back in here. I will replace this. So my expression on the left, so therefore my expression on the left was x square minus 3x minus 4. It becomes a, which is 1 by 5 over x minus 1, no, plus 1. What was that? A was 1 by 5, no, a was minus 1 by 5, sorry. This is minus, right? A is minus 1 by 5 and b. So my first expression, this is equal to this one. No need to write the middle one now. Okay. So a and b, if I replace the values, a is minus 1 by 5 and b is 1 by 5. So now I can integrate. You see, now if you want to integrate, it will be just one step answer. So therefore, the integration of the left hand side is minus 1 by 5 is constant. I can write it outside. Integral of 1 over x plus 1 dx. Then again, this 1 by 5 is constant. I write it outside. Integral of just 1 over x minus 4 dx. Okay, so this will become minus 1 by 5. Because the derivative of this is 1, which is given over there, I can write log of x plus 1. Plus 1 over 5, again the derivative of this is just 1, which is given over there, so I will write log of x minus 4 plus a constant. So this is your partial fractions, okay? And partial fraction technique, and just to make it easy, I will just give you the linear factors in the denominator. In the denominator there are linear factors, it's very easy. So what formula I used here? If you have any linear expression ax plus b, okay, dx, you can use this formula directly, that it is log of ax plus b, log of the denominator. But if you have this a here, you divide by a outside. This is the formula that I used. So see, there is no a in both the factors. A is 1 in both your, you see here, a is 1. So b has no contribution in your answer. So whatever you have in the denominator, linear factor, it goes to the log. Linear factor, it goes to the log, okay? If it is linear, it goes to the log, and if you have any number here, 2, 3, 4, it will come down here. For example, if I write 1 over 3x plus 2 dx, it will be natural log of 3x plus 2 plus constant, but because I have this 3 here, so I will divide 1 over 3. Okay, this is the only thing you have to do. If there is no 3 here, I will not divide by anything. So you can use this formula directly here at the end of 7.4. Okay guys, so I think I have covered almost everything. So I am not saying that just look at this review. You should look at the notes that I did in during the lectures. You should look at those examples as well, because I did lot of them. Okay, so I hope this will help, and I will be available in my offices tomorrow, day after tomorrow, so before the exam. So if you have any questions, anything, you can come visit my office, or you can, if you are not here, far away, then you can send your question in my WhatsApp as well, or email me. I will try to answer as much as possible. Okay, so will this session help? All right guys, if you have more questions, you can ask. If no more questions, yeah, sure, I will upload this on Moodle, okay, and the recording as well, don't worry. All right, okay guys, see you inshallah. I hope this will help you, and if you have any questions, you are always welcome. See you inshallah. Good luck. You're welcome.